So we have experimental curve that looks, let's say, like that. Okay? If we draw the slope line, okay, here would be the corner. Here is the full delta y. I take 63% and I come to the orange line. This is going to be the 63. You understand? So I'd like to take 63%. Okay? That's P63. And this distance, tau, is now going to be P63 minus P. In other words, P63 replaces the do not use time. And now you're guaranteed that the model will exactly pass through this point. I'm also guaranteed that the model will have the correct steady state. So the model will give me a proper curve that stays flat until the corner, takes with that slope, passes exactly through the orange line at this point, and passes exactly at the new steady state. This forces the purple line to be down close to the orange line. Well, if I had used the do not use method, what would I do with the do not use method? Here is the do not use time. Okay? That gives me a larger time constant. The do not use method would have given me a curve that looks like that. Much further from the orange line. You understand it, guys? All they know?
Is that the furthest we can match exactly with the experiment? 63%?
It's one point we can match. We can choose actually any point we want. The classical slope method uses that point, but as you will see from all the examples, you can use other variants.
Why do we even consider the do not use method?
Because it's in all the books. Because if you read the last article in chemical engineering application of controller tuning, they will just have the do not use method. That's why. Most books have only the do not use method. I wish that wasn't the case, that wouldn't be. And conceptually, it's not that much more time to discuss it. But since you're going to be saying it in books, I wanted to discuss it. And I also assign it homework for you to compare how the two different methods do. Okay, doing okay, guys? So, that's the slope method. So it gets, slope method gets K as all methods delta y over delta u. It gets the time delay exactly the same way as the do not use method, by drawing the slope line and see the intersection of the slope line with the original steady state. But instead of using the do not use time, it uses the 63% time. You see, 63% from the new steady state is where I'm going. Before I abandon, let me do one more example.
Wait, can you, what is the, tau is what? I
You
almost
get
have
tau from the distance between T63 and tau constant, and T coordinate, sorry, T63 and T coordinate, instead of T do not use minus T coordinate.
So tau is the time it takes to reach
Time is
63%.
the distance between T63 and T coordinate. We saw that
No, but
with time T naught plus D plus tau, which is T coordinate plus tau. If I use time T coordinate plus tau, I go 63% of the
okay,
distance
that's
to
what
the
it
new
is.
steady state.
That's what it is. Okay.
One quick example also. Suppose that I have a response curve that went down. Let's use the slope method. So I'm drawing a nice slope line. That's not a nice slope. Okay, that's a response. Here is the entire delta y. Here is T coordinate. Let's say T naught. So this distance here is the time delay. So for 63%, I take 0.63 delta y. Kirling delta y. Don't write it, okay?
Don't write it.
Don't write it. What did I do wrong? Let me go with Robert.
You took 68% from the bottom.
Exactly. Remember, it's 63% off where I start from. I start from up here. So that's incorrect. The correct one is 0.63% from this point.
So sneaky.
Careful not to mess it up.
Sneaky.
I'm seeing a couple make that mistake in exams. So here is the correct P63. Okay, careful. P63 is 63% towards the new steady state from where you start. So as I mentioned previously, when I first started at UF, Exxon held a workshop and they invited faculty members for teaching process control to discuss about teaching process control, and they showed us how they tune controllers. And basically, they just directly went first order plus time delay model, but they didn't use either of those two methods. They used a method that I had never seen before, but then I saw the Smith-Corribio book and I realized it was a variant of the same method as in the Smith-Corribio book. Here's the idea. I have three parameters to choose. K, tau, and D. K, by choosing delta y over delta u, matches exactly the steady state. That's critical, that's a lot of points, right? Steady state is infinite points. So that's very important. K has to be delta y over delta u. I have two parameters, tau and D left. What if instead of drawing a slope line, we simply match exactly experimental data and model in 2 points? Okay, instead of the slope line matches exactly at the T63, at 63% of the new steady state. Let's match exactly at 2 specific points. Exxon, their method was matching exactly 75% towards the new steady state and 25% towards the new steady state. So forget about slope line. I have 2 parameters to play with, tau and D. Determine tau and D by matching exactly model response and experimental data at 2 particular points. Exxon uses 75% and 25%. The Smith-Corribio book, staying close to the slope line method, and doesn't have a name, but it has the slope line method there. Okay, matches exactly 63.2% and 28.3, I believe, which is the time which you do tau over 3. It's T corner plus tau over 3, you get 28.3% of the steady state. About 28%. I'm not sure, it might be 28.1. 28% steady state. That's for sure 2 digits cycle. So the idea is we match exactly 2 points for tau and D. And we're matching exactly the steady state. So we're matching exactly 3 points now. No slope line drawn. And we match exactly 3 points. One always must be the steady state. That's much more important than any other point. And then the other 2 points you can choose. Exxon uses 75% and 25%. Smith-Corribio 63 and 28. We can have the, I'm murdering your last name, Felix. Crispian? Okay, we can have the Felix method,
Okay.
and Felix may choose to match exactly 70% and 30%. And like it is, we will see, we have to solve 2 very simple linear equations to find tau and D.
Can you draw it? It's really hard to follow you.
Yeah, I'll draw it. I'll
Yeah,
explain.
I'm
Yeah, okay. So, I have an experimental response curve, right? I have 3 times K tau and D. I'm playing with the first order plus time delay curve that will have this with the corner, this kind of shape. Well, I'm going to use my 3 parameters to exactly match the steady state and 2 other points. And I can choose where I want to match the 2 other points. I could choose to match them here and here. I could choose to draw to match them here and here, for example. Okay? The idea is I match My model, the white line, experimental data, orange line, are 2 points in addition to steady state. I call this the 3-point method. I'm including steady state as a point. So I'm matching exactly 3 points. And yeah,
When you say 75, 25, what do you mean by that?
to what distance towards steady state. So here we travel. Okay, what is the action method? The action method is the following. So action method, you do a step change, you get your response curve. Here is your delta y. You take 75%, so 3/4 of that distance. That gives you T75. You take 25%, 1/4 of that distance. That gives you T25. You get K as delta y over delta u, and you get tau and D from T75 and T25. And we'll get it, we'll do that today. Okay? So let's move towards the action method. No, the 3-point method. We'll see in a minute. Okay, so I want to do the Smith-Corrigan method first because that's closer to what I've been doing. You prefer the action method first? Okay, I'll do the action method.
And that's method number 3.
Yeah, method number 3 is 3-point methods where you can choose what are the 2 points in addition to steady state. So method 3. Again, the names are mine. Smith-Corrigan didn't name them, so. So the key is the 4-star equation. Y, and I can write either prime or y. Can I work with y prime, guys, okay?
Yes.
Y prime is right. So y prime is 0 for t less than t naught plus d. And k delta u, 1 minus e to the minus t naught plus d, all that divided by tau for t greater than t naught plus d. That's the key. So, experimentally, I measured T75 and T25. Okay, I have my experimental data. Okay, so when will the model be predicting that I am at T75 at 75% of the steady state? Y prime must be 0.75 delta u, delta y, sorry, at to exactly match experimental data at T75. I must have Y model at T75, or Y prime model at T75, equals 0.75 delta y. Because that's how I get the experimental point. I take 0.75 delta y. Okay, this is 0.75 delta y. I write y. So at that time, I must be 0.75 delta y. So if my model is at this point, the model exactly matches the experimental data. Clear, everyone? Sorry? Okay, if at T75, at 0.75 delta y, I'm exactly matching the experimental. Okay? So, how do I achieve that? Well, I have this equation. So I must have y prime model must equal 0.75 delta y, and is equal, according to that equation, to k delta u, 1 minus e to the minus t minus t naught t75. This t now is not anything, it's t75. At time t75, I must be equal 0.75 delta y. Okay, let me emphasize, this is now t75 minus t naught plus d divided by now. So I want at time t75, the model to be giving me 0.75 delta y.
Yeah.
I don't want to go forward until this is completely understood. Mika. Okay. David. Daniel. All right. Now, k delta u is what? We always fix k to be delta y over delta u. So k delta u is equal to delta y. So delta y cancels. So now let's work with this equation. Follows that 0.75, 0.75 equals 1 minus e to the minus t75
Are you solving for tau?
minus t naught plus d. You won't be able to solve for one. We'll have to solve two equations that have both ones. Right? That's what I must do. Delta y cancels out. That's what I'm left. I can put the exponential on the other side, the 0.75 on the right-hand side. So from here follows that e to the minus t75 minus t naught plus d divided by tau is equal to 1 minus 0.75, which is 0.25. Follows. Let me write the other word.
What the hell?
Take the natural log. So take the natural log minus the bracket, which is t75 minus t naught plus d, all that divided by tau, is equal to ln of 0.1. Or this gives me minus t75 minus t naught minus minus t naught, and then I have minus d, so plus d equals tau ln 0.25. Just move the tau here. I group these two together and I left d apart. So
Shouldn't that be plus?
no, minus the same as plus, but I left it together with t75. Okay, if I wrote it without the minus, it would have been minus t75 plus t
No, I
naught
get
plus d.
you.
So I get the equation, and I'll give it a number, that d minus ln of 0.25 times tau is equal to t75. I move this to the other side, I move this tau. Yeah. Is equal to 275 minus 2. So I move this to the left, and I move this to the right. So d minus ln 0.35 times tau equals 375 minus 2. Call this equation. What kind of equation is that? It's a linear equation with respect to the variables d and tau. T naught is a number, whatever time I change. T75 I measured from the graph, so I measure with the orange line. Okay, that's a number. It's a linear equation for two unknowns. Obviously, I cannot determine two unknowns with one equation. But that's